original DFA. Well, it has of course to do, but it is definitely different. And so I start out 0, 1, 2, 3, 4, 5, 6, 7. This is my starting point. And then, as before, I have all the accepting states, 0, 2, 4, 6, and all the rejecting states, 1, 3, 5, 7. And I draw this line here all the way to the bottom to indicate that once they're split, because once I split them when I know they can be differentiated. So obviously all accepting states can be differentiated from all rejecting states. So what that means then is I have to go through the same process as before, and so I take 0 and I compare it with 2. 1 under A is 1 and 3. 1 and 3 are together, and under B is 2 and 4. 2 and 4 are together, so 2 and 0 cannot be differentiated from each other. Then I go 2 and 4. Under A is 3 and 5. They're together. Under B is 4 and 6. 4 and 6 are together, so I can't differentiate 4. And finally 6. 6 and 4. 4 and 6. 4 under A is 5. Under 6 under A is 7. 5 and 7 are together, so I have to go to the next state, next letter, which is B. 4 and 6 is 6 and 0. 6 and 0 are together, and therefore I have not been able to differentiate anything in here. And then I go to the next equivalence class, 1, 3, 5, 7, and I take 1. 1 has to be somewhere, and then I see whether 1 and 3 can stay together. So 1 and 3 under A is 2 and 4. 2 and 4 are in the same equivalence class, therefore nothing there. And then under B, 1 and 3 is 3 and 5. 3 and 5 are together, so 1 and 3 cannot be distinguished from each other at this point. Then I take 5, say 3 and 5. 3 and 5 under A is 4 and 6. 4 and 6 are together in this equivalence class. And under B, I have 3 and 5 is 5 and 7. 5 and 7 are in the same equivalence class and therefore cannot be differentiated from each other. Then I have 7. 5 and 7. 5 and 7 is 6 and 0. They are together, and therefore no differentiation of 5 and 7 at this point. And then I have B. 5 under B is 7. 7 under B is 2. 7 is here. 2 is here. So 7 has to be split off, because I can differentiate 5 from 7. 5 from 7, as I said, I use B. 5 under B is 7. 7 under B is 2. And so that means this is my B. The P is 5 and the Q is 7. The A is B, so P sub A is 7 and Q sub A is 2. So I have 7 and 2, and now looking at the fact that 7 is in this equivalence class and 2 is in a different one, means that 7 and 2 can be differentiated. So this is then how we know that P and sub A and Q sub A are differentiated because they're in different equivalence classes. So I'm not really looking for that W, I'm just looking for the fact that P sub A and Q sub A are in different classes, which means I can differentiate them. And so that is the situation that I have here. I have 5 and 7. Under B is 7 and 2 is here, and 7 is here, and therefore 5 and 7 cannot be kept together. And now, of course, I have a problem because this equivalence class is different from that equivalence class. The second row consists of 2 equivalence classes. The third row consists of 3, so clearly they're not the same. This is very different from what I had up here, where the second row and the third row were identical. So that meant that the 2 equivalence classes were in fact identical. In this case, that's not true. The second row consists of 2 equivalence classes. The third row consists of 3 equivalence classes. Obviously, therefore, they're not the same. So I have to continue. Well, let's take 0 again. And 0 and 2 is 1 and 3 under A. 1 and 3 are together. And under B is 2 and 4. 2 and 4 are together. So that's okay. We always look at the last completed equivalence class, the last completed row. So 0 and 2 cannot be differentiated at this point. 2 and 4. 2 and 4 is 3 and 5. They're together. Under B is 4 and 6. They're together. So 2 and 4 can't be differentiated. Then 4 and 6. 4 and 6 is 5 and 7. You're looking at 5 and 7. Well, that means that under A, 4 and 6 can be differentiated because there's 5 under A and there's 7 under A. And so 6 has to go somewhere else, cannot go with 4. And the only other place it can be is that it has to go into its own new equivalence class. So 4 and 6 at this point can be differentiated. Okay, so 1 has to be somewhere. 1 and 3 is 1, 2 and 4. 2 and 4. We always look at the last complete one. 2 and 4 are together, so nothing here. 1 and 3 under B is 3 and 5. 3 and 5 are together, so that is that. No differentiation. 3 and 5. 3 and 5 under A are 4 and 6. 4 and 6, as I said, we look always at the last complete equivalence class, not what is down there, because that would change things. So if eventually they split, then they split, but at this point 4 and 6 are still together in the last complete equivalence class, and therefore under A, 3 and 5 cannot be differentiated. 3 and 5. Under B is 5 and 7. Well, 5 and 7 are in different equivalence classes, so 5 cannot stay together with 3. 7, of course, is a single element, so no big deal. We don't have to do anything. Obviously, we can't cut the 7 into 2 halves, so it's just on its own. Then, obviously, this last completed row is different from the one before, therefore we have to continue, so 0. And then 0 and 2. 0 and 2 is 1 and 3. 1 and 3 are together. Under B is 2 and 4. 2 and 4 are together. So 0 and 2 cannot be differentiated at this point. So let's take 4. 2 and 4 is 3 and 5. Well, 3 is here, 5 is here, so 4 has to be split off. Cannot be merged, cannot be kept together with 2. 6, of course, is a singleton. 1 has to be somewhere. So let's see, 1 and 3 is 2 and 4. 2 and 4 are together in the last completed equivalence class. And 1 and 3 under B is 3 and 5. 3 is here, 5 is here. So 3 has to be split off. 5, of course, is alone, 7 alone. So we have this equivalence class. And then the only thing where anything could happen is 0 and 2. So 0 has to be somewhere. 0 and 2. 0 and 2 under A is 1 and 3. 1 is here, 3 is here. So 2 has to be split off. Everybody else is, of course, already singleton, which means that this, the red DFA, is already reduced. So that automaton, the second one, the one where I changed the result of the state 7 under B to 2, that now is a DFA that is already reduced, so it is the unique smallest DFA for the language accepted by that deterministic finite automaton.
Professor, I have
Yes.
a couple of clarifying questions.
Sure.
So on this second exercise we did, we're just double checking that this DFA that was presented to us was an actual reduced DFA.
In the second, yeah,
yes,
that was the outcome of carrying out this process, where we ended up with all new states consisting of exactly a single old state, in which case it means that the old DFA is in fact the smallest DFA you can have.
Okay. Does this actually answer any question in terms of like division or anything? Like, is the reducing, is it important for us because it will later on be important to make more complex languages, or is it important because the reduction helps with storage?
Two yeses. The first one is yes, of course, the smaller things are, the better it is for you. If you can get the same functionality with a smaller automaton, then you probably should use that. However, as I indicated, one way in which you need the reduced automaton is if you want to answer a question. Here are 2 regular languages. I give you 2 regular expressions, and you construct the corresponding DFAs for those 2 regular expressions. Do these 2 regular expressions denote the same language? Well, the only way in which you can decide that is by constructing for each of those 2 DFAs the reduced automaton, and then you compare the 2 reduced automata, and if they are identical up to renaming of states, then the original question is answered in the positive. The 2 regular expressions are in fact denoting the same language. If the 2 reduced automata are not identical up to renaming of states, then the answer is no, they're not. So you have 2 aspects. One is, yes, obviously there are advantages to keeping things as small as possible. So you may have a part of a compiler that recognizes tokens, keywords, and so on. You want to keep that part, which is tip of the compiler, which is typically automata-based, as small as possible. you want a reduced automaton. But at the same time, there are also theoretical issues. So if you want to test whether two languages, say you have two regular expressions, alpha 1 and alpha 2, well, it'll give you two languages. L sub I is Ri. So the language denoted by alpha 1 is R1. Language denoted by alpha 2 is R2. Are they the same? They can, different regular expressions can denote the same language. But how do you test that? Well, if you want to do that in a systematic way, you basically have to construct the corresponding DFAs for the two regular expressions, then reduce these two DFAs and compare them whether they're identical up to renaming.
Professor?
Yes.
Without spending too much time on it, would you provide again a definition of what is renaming of states? Because I missed that.
Oh, this is kind of trivial. I mean, if I call these 0, 1, 2, 3, 4, 5, 6, 7. Well, if I call them Q0, Q1, QT, and Q7, then nitpickingly, mathematically, these would be different states. Right?
Okay.
That's all it is. If you want to say they're the same, then they're, for all practical purposes, the same. But from a mathematical point of view, you have two sets of states. Q, there. This Q, well, if I change a state and give it another name and systematically work with that, then theoretically this is a different automaton. But that's just very nitpicking. So
when you're making the table at the end, where in the case of the reduced automaton, and you're calling it simply P and Q and
right.
eliminating the rest of the numbers.
If I called it capital A and capital B, then theoretically that would be a different automaton. But obviously it's the same for all practical purposes.
So it's just ease of use, like whatever is convenient.
Yes.
Thank you.
Sure. Any other questions?
Professor, can you give one more example where
that's already planned. In fact, what I'm going to do is I'm going to take the whole process. Start with a regular expression. A, B star A, union C, A star.
If I
Yes?
may, I wanted to have an example where the expression isn't reduced on its own. Like we did two examples, and at the end the result was that they were already reduced, so we cannot do any more. But is there any example where the actual expression isn't reduced and we can reduce it after using the process? So if you can...
Well, I gave you two examples. I gave you one automaton where it reduced to two states, and I gave you another automaton where no reduction was possible.
All right, I'm sorry I missed that.
Okay, but let me give you this example: A, B star A, union C, A star star, and let's do the construction of the NFA, the construction of the corresponding DFA, and then the reduction of the DFA. So we have, in this case, there are three letters, A, B, C. So 0, 1, 1, nothing, 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 0, 1. So this is for A, and 0, 2 for B, A, B, C, nothing, 2, nothing, 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 0, 1. And then 0 is, of course, always the initial state. and then we have 0, 3 for that A, B, C, 0 goes to 3, nothing, nothing, so 3 goes to nothing, nothing, 0, 1, so that's that A. Then we have that C, 0, 4, A, B, C, nothing, nothing, 4, nothing, 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 0, 1. And finally that third A, the last letter, 0, 5, A, B, C, 0, 5, A, it's 5, nothing, 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 0, 1. Okay. So that means now we can, well, how many operations can we do?
Should we begin with the star operators in the inner parentheses?
Well, I think that's the only thing you can do. There's this star operator B star or the star operator A star. Nothing else you can do. Everybody clear? There is no other operation that could be done at this point. You can only do the B star here or the A star here. So let me do that star, B star. So what do I have? Obviously, I have the same set of states using the star construction, same set of letters, obviously. Final states, well, everything old final plus the initial state must also be final, so that means both of them are. And now 0 in the initial state of the old automaton is rejecting, so we just copy. And 2 is accepting, so we take the union of this row, of the row nothing, 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 with the initial row, nothing, 2, nothing, so this is nothing, nothing is nothing, 2 and nothing is 2, nothing, nothing is nothing, nothing, 2, nothing. So this is B star. And now, how many operations can we do?
Three.
Correct. We could do this concatenation, or we could do this concatenation, or we could do this star. Those are the three that we could do. Let me just be unimaginative and go strictly left to right. So I'm going to do this concatenation, A with B star. So this is concatenation. Set of states is, of course, the union 0, 1, 2. A, B, C is the alphabet. The initial state is, of course, 0, as always. And now we have to get the final state. So we have to look at what is the initial state of the second automaton. It is accepting. Therefore, we take all the final states of the first automaton plus all non-initial final states of the second automaton, which means the 0 is rejecting and 1 and 2 are accepting. Okay? And now we have this is rejecting, 0 in the first automaton, so we just take that row and copy. 1, nothing, nothing. 1 in the old first automaton is accepting, so we take the union of this row with that initial row, which is nothing, union nothing, nothing, union 2, nothing, union nothing. So this is nothing to nothing. And the second, the state 2 is in the second automaton, so this is always copy. So this is now the concatenation of those two automata. And now we can do the concatenation of those two, the automaton for A, B star, and the automaton for the second A. So we have 0, 1, 2, 3. A, B, C. Final states, well, what do we have? The second automaton has a rejecting initial state, which means we only get the final states of the second automaton. Everything else is rejecting. And now we do the transition function. Well, this initial state is rejecting, so we copy 1, nothing, nothing. 1 is accepting, so we take the union of nothing to nothing with the initial row 3, nothing, nothing, so this is 3, 2, nothing. And the same thing for 2. 2 is accepting, so we take the union of the row nothing to nothing with the row 3, nothing, nothing, which is 3, 2, nothing. And the state 3 is in the second automaton, so this is always a copy. So this is now the automaton for A, B star A. And now I can do the star. That's the only thing I can do for that A. So this is 0, 5, of course, and A, B, C. And final states are 0. Both states are final. So that is 0 and 5 are accepting. And then the initial state is rejecting, so we copy. 5 is accepting, so we take the union of this row with that row. So 5 and nothing is 5. Nothing and nothing is nothing. Nothing and nothing is nothing. So this is A star. And then we can do the concatenation of those two, which is 0, 4, 5 for the states, and A, B, C. And so the initial state of the second automaton is accepting. So that means we get all the final states of the first automaton plus all non-initial final states of the second automaton, which means 4 and 5 are accepting and 0 is rejecting. And then finally, the transition function, 0 is rejecting in the first automaton, so it is nothing, nothing, 4, union 5, nothing, nothing, so this is now nothing, 4, nothing, look, 5, nothing, 4, so the union of nonsense. We're concatenating. Hold on. What am I doing? I'm doing the concatenation of this with that. This is rejecting, so this is just copy. Sorry. I knew I was screwing up. 4 is accepting, so we take the union of this row with the initial row. That's 5, nothing, nothing. And 5 is in the second automaton, so that is copy. So this is the automaton for C, A star. And finally, well, not quite finally, we can do the union of these two. So this gives me 0, 1, 2, 3, 4, 5. A, B, C. And this is the union, so the only place where there is a union to be carried out of rows is for the initial state, so we take 1, nothing, nothing, union, nothing, nothing, 4, which is 1, nothing, 4. Oh, the final states, of course, are all the final states we've had. So 0 is rejecting, 1 is rejecting, 2 is rejecting, 3 is accepting, 4 is accepting, and 5 is accepting. And then we've done the union of 1, nothing, nothing, and nothing, nothing, 4, which is 1, nothing, 4, and everything else is copy. 1 is 3, 2, nothing. 2 is 3, 2, nothing. 3 is nothing, nothing, nothing. 4 is 5, nothing, nothing. And 5 is 5, nothing, nothing. And with that, the last step then is the star, this star here. And so we have same set of states, 0, 1, 2, 3, 4, 5. And A, B, C. Final states are all the old final states plus the initial states. So 0 is accepting, 1 is rejecting, 2 is rejecting, 3, 4, 5 are accepting. And, well, the transition function, 0 is rejecting, so we copy 1, nothing, 4. 1 is rejecting, so we copy 3, 2, nothing. 2 is rejecting, copy 3, 2, nothing. 3 is accepting, so we take the union of that row with the initial row, so this is nothing, 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 union 1, nothing, 4, which is 1, nothing, 4. And then 4 is accepting, so we take the union of 5, nothing, nothing with 1, nothing, 4, which is 1, 5, nothing, 4. And the same thing for 5. 5 is accepting, we take the union of 5, nothing, nothing, with 1, nothing, 4, which is 1, 5, nothing, 4. And that is now the reduced, the NFA for that regular expression. And now we can do the deterministic finite automaton. Start with 0, 1, nothing, 4. One, nothing, 4. Nothing is, of course, a state that has to be considered, and therefore we have to write it down. So 1 is 3, 2, nothing. 3, 2. Nothing is nothing, nothing, nothing. 4 is 1, 5. Nothing, 4. 1, 5. 3 is 1, nothing, 4. 1 and 4, all of them already there. 2 is 3, 2, nothing. We have 3, 2, and nothing. 1, 5 is 1, 3, 5. 1, 5 under B is 2, and 1, 5 under C is 4. And then 1, 3, 5 is 1, 3, 5 under A. 1, 3, 5 is 2 under B. And 1, 3, 5 is 4 under C. And so the deterministic finite automaton is this, and we still have to determine what are the final states. Well, obviously 0 is, 1 is rejecting, 0 is accepting. Why am I saying? Okay, 1 is rejecting. the set of state is always rejecting. It doesn't contain any state, so in particular it doesn't contain any final state. 4 is accepting, 3 is accepting, 2 is rejecting, 1, 5, 5 is accepting, so 1, 5 is accepting, and 1, 3, 5 is accepting. So this is now the corresponding deterministic finite automaton. And now it probably is a good idea to actually rename that. So I am going to do well, let's see, I'll call this A, B, C, D, E, F, G, H. So A, B, C, D, E, F, G, H, because otherwise you're going to get confused with the reduction algorithm. So A goes to 1, which is B. 2 is empty C, 4 is D. B goes to 3, which is E. 2 is F, and that is nothing is C. C is of course C, C, C. D is 1, 5, which is G. Nothing is C. 4 is D. E goes to 1, which is B, C, and D. F goes to 3, 2, nothing, which is E, F, C. G goes to H and F and D.
Excuse me, Professor?
Yes?
Did you forget state 5 in the DFA?
No. Why would I forget? What I do is I write down what I encounter.
Oh, okay.
And since I don't encounter the state 5 alone, I don't write it down. It is completely useless.
Okay.
I do have 5 reflected there. It has a functionality, but it only occurs in conjunction with 1 or with 1, 3. 5 alone does not exist. And since I only write down what I need, I don't write down 5. Is that clear?
Yes.
Well, no, this is important. This is important because you can, of course, write down all subsets, in which case, in this case, you would have 2 to the 6 different subsets to consider. That is more than overkill, that is suicidal, because the automaton, instead of having 64 states, has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's important. No, I did not forget 5. Absolutely not. I write down what I need. And since 5 does not occur,
Do you treat like 1 and 5 as one single state then?
Yeah. Why do you think I call it G?
Yeah, yeah, because you need one single state.
It's a single state now. This is the same thing. I'm simply renaming that old DFA. Okay, there it is. This is now the new, the DFA with states renamed, and now it is perfectly obvious that indeed this is a DFA. It may not be entirely obvious to you that this is a DFA, but this clearly is a DFA, right?
Right.
So again, maybe you weren't gesturing with your mouse pointer, but I understand what you were referring to.
This is the DFA that I obtained from that NFA by simply going through the way in which I write down each state as it arises. So from 0 I go to 1, nothing, 4. So 1 is written down here as the next state. Then the next state is nothing, which is written down here. And then 4 is written down here. And so this is a queue of states that need still to be considered. And then I consider each state at its time. And if I encounter a state that I haven't considered yet, it will be added to that list. So 1 under A is 3, so 3 hasn't been considered yet, so it's going to be written down. 1 under B is 2, which I haven't written down, so 2 goes down here, and nothing I have already, so that is that. And then I go to this, nothing goes to nothing, nothing, nothing. Then 4 goes to 1, 5, which I haven't written down, so there it is. And under B it goes to nothing, so that there it is. And 4 we've already written down, and so on and so forth. Everybody clear?
I see what happened. Like, state 4 in like the NFA is like the same as state 5, so you didn't have to write state 5 down.
No, that has absolutely nothing to do with it.
Oh, never mind.
No, you're not listening to what I'm saying. Okay? You write down every state that is encountered. There is no 5 anywhere in this. There is 1 5, which I did write down.
Yes, sir.
But there is no 5. Therefore, there's no business writing down 5 here.
So I think what the professor is illustrating is that when you're creating the DFA, you go iteratively from the very beginning, the initial state of the NFA, and then like he said, every state you encounter, you then write down those states on the left-hand side of the DFA, and then like expand iteratively outward until you've like expanded all you can.
Well, no, you don't expand. You simply generate new sets. And as long as you haven't considered everything, you have to continue. But eventually you will run out. So in this case, we ran out after we did 135, because 135 is 135, 2, and 4, and all of these we have already considered.
Yes, thank you.
Okay? And now, because what we basically have to do is write these equivalence classes down, and if we do that with those sets of old states from the NFA, you get confused. So you actually have to rewrite the automaton, the deterministic finite automaton, so that it does not any longer reflect these sets of states from the NFA, but you just call it new states. A, B, C, D. Oops, what happened here? Why are you moving?
Control C, Professor.
Control Z. Okay. Thank you. Undo whatever nonsense it insisted on doing. Okay, so now we have to do...
Professor?
Yes.
I have a little one question. Like the process from the beginning, so is the process should be the same exactly we did right now, or like, for example, we did B asterisk, right? And then we did B concatenation with A. I mean, no,
Okay.
yeah,
It makes no difference.
okay.
You remember I said when we said which operations can we do? So I did this concatenation. Well, obviously first I did the B star, so that gave me this.
So
Then I
like,
did concatenation A B star, that gave me this, and so on and so forth. If you do it in any other order, if you had started with the A star here,
mm-hmm.
which would be this, and then you had concatenated the C with the A star, that would have given you here, and so on and so forth. You would get exactly the same non-deterministic finite automaton.
Okay, thank you.
The order in which you apply the legal operations is entirely irrelevant, as long as you start with the basis where you assign a number to each letter. So this is the first letter, this is the second letter, third letter, fourth letter, fifth letter, and then the first letter corresponds to 0, 1, the second letter corresponds to 0, 2, the third letter corresponds to 0, 3, the fourth letter corresponds to 0, 4, and the fifth letter corresponds to 0, 5. As long as you do that, the order in which you carry out the various operations, concatenation, star, and union, is entirely irrelevant. The result is going to be exactly the same.
Okay, so also like 0 and 1, 0 and 2, so we just assume that, right? The entries.
Yeah, because you remember the stipulation was you had to have, well, Q alpha intersection Q beta is only the initial state. So they can't really have anything in common other than the initial state. So that 0, of course, is always there, but everything else has to be different. And the easiest way to achieve that is to simply do, this is first letter, second letter, third letter, fourth letter, and fifth letter, and then you have 0 plus the number that corresponds to the number of the letter.
Thank you so much.
And now how am I going to do that? Well, I'll have to write it down again. A, B.
You could copy paste it, Professor. So the same way, yeah, same way that you can grab it, grab the red, click on it, like the way that you had done earlier. No, not on that one, on the actual PowerPoint itself.
Oh, on the PowerPoint, okay. So I do this.
Backwards. You would have to go from the bottom right to the left.
From the bottom right to the left, like this?
Yes.
And now I do a copy.
Yeah, Control C.
Yep.
And then now you can Control V over here.
See, I have no idea about those PowerPoint things. Okay, I guess we can just start that again. Come on. Oh, whatever. How do I move that now?
Control Z, when you Control V, it should keep it selected, and then you can move it. Control Z to undo, and then Control V to paste it again.
Paste it here. No.
So it's still selected. See how it's all selected? Now just click and drag it over to where you want it. You want to click where just Control Z again. Let go and Control Z.
And then click where? Down there?
On top of the edge, like where the edge is at. See how it's got the 4 directions? That means you can move it. There. Oop.
There?
Oh, no. That's going to resize.
Yeah, don't click on a point. Just click in the middle in an empty
Yeah.
spot.
Click on the line, on the lines of the rectangle. There you go.
Ah, okay. Thank you very much. Okay, all right. So this is now the same. Well, we copied it, so it should be the same of the NFA. And now we have to go through the process of doing this reduction. And so we have start out with A, B, C, D, E, F, G. And now we split it up into accepting and rejecting states. So A is accepting, D is accepting, E is accepting. I forgot H. Ah, there. Thank you. All right. Thank you. Thank you. Somebody pays attention. A, D, E, G, and H. And we have B, C, and F.
Just to make sure, is this the DFA or NFA?
You are right. It is the DFA. Okay. All right. I guess. All right. So now with the reduction. Well, A has to be somewhere. So we write it down. Then A and D is under little a is B and G. B here, G here. So D has to be split off. Okay, so in this case it was just for the first letter already. A and D are going to be different because it's B under from A, which is rejecting, and G from D, which is accepting, so they're different. So we got A and D. Now, E. E could go together with A. If we can keep it together with A, we don't have to do anything else. On the other hand, if it can't be together with A, then we'll have to try D. And if that fails as well, then we'll have to put it into its own equivalence class. Okay, everybody clear? So let's try E with A. E with A. Well, let's try E with D. It doesn't make any difference because E with D, E and D is G and B. G here, B here, so E cannot go together with D. So let's try the other one. A. E and A is B and B, C and C, and D, so obviously A and E are going to stay together. Now we have G. G could go with AE. If that fails, it could go with D. And if that fails, G will have to go it alone. So let's take G and A. We can pick any one of them. So B and H. B and H, so that fails immediately. G and A cannot be together, so G can't be with AE. So let's see whether G can go with D. G and D is G and H. G and H are together. G and D is C and F. C and F are together. And D and D, so G and D can go together. Everybody clear? Let's go through that again. D and G. D under A and G under A is G and H. G and H are here together. Then we have under B is C and F. C and F are together. They're in the same, just because they happen to be, this happens to be a different equivalence class from the one under A, doesn't make any difference. They are together. That's the main thing. And then, of course, under C, D and G are both D, so there is nothing interesting. So we finally
Still
have...
not entirely clear. When you say they're together, are you referring to the fact that they're either both accepted or both not accepted?
No. It's not a question of acceptance or not. That in this case it happens to be that way, but in general it is just they're together in some equivalence class. So if you have this...
But how are you determining that they're... I thought you were trying to determine if they're together in an equivalence class.
In the last equivalence class. You look at the last row, and if they are together there, then you're okay. And if they're not together, then you continue. So you have H, G and H. G and H is H, H under A, under B is F, so that goes together. All right, then we have B.
Wait, Professor, one more time. So G, I'm looking at G and H. So in G, for A, I have H. And then in H, for H, I have H.
Right, so they're the same. So you don't really have to check whether they're in the same equivalence class, because they're the same.
Mm-hmm. Okay, so
you can go through the motion, and obviously you have H here, and then you have H here, and they're in the same equivalence class, and then you go on. Then you have F and F, they're in the same equivalent class. Then you have D and D, they're in the same equivalence class, and therefore they stay together.
Okay, so what am I looking for whenever I'm looking at H? So like G, like I'm comparing G and H, right? That was the last comparison you made.
A, and then under the letter B and under the letter C, and you check whether those states that result are in the same equivalence class or not. In this case, it's trivial because G under little a is H, and H under little a is H, so they're obviously in the same equivalence class because it's the same state. The same thing for F and F, same thing for D and D.
Got it.
Okay.
So does that mean that if we're gonna go with B right now, which you compare that one to C?
Correct.
Right, and
B
so
and C is E and C. E is here, C is here, so we fail immediately.
Wait, can we stop there? So like you looked at C, C is all C's, B is...
I look at B and I look at C. I look at the first letter, A. You have E for B and C for C. Okay? E is here. C is here. They're in different equivalence classes, therefore you can't keep B and C together.
Okay, I believe I got it now.
All right? And then F, well, it could go with B. If that fails, it could go with C. And if that fails, then it has to go it alone. So B and F. B and F. B under, so we have E and E. B and F. We have E and E, so that obviously is nothing particularly interesting. Under B is F and F. Okay, same thing. C and C, same thing. So B and F stay together. So this is now the equivalence class that we've constructed. And now we have to continue because obviously this is different from the one before. So A has to be somewhere. A and E is B, C, D, and B, B, C, C, D, D, so A and E stay together. So that's that. Then we have D somewhere, D and G, D and G is G and H, that's together, G and H. D and G is C and H, C and F, that's not together, so G has to be split off. And then we have H, go with D. D and H is G and H, that's fine. D and H is C and F, C here, F here, so no. That means we now have to try the next one because we've done D, and that doesn't work. So let's see whether it can go together with H. Well, G and H under A is H, F and D, so obviously that stays together. And finally B, and try F, B and F, B and F. Well, you can see that B and F under A is E, B and F under B is F, B and F under C is C, so B and F stay together. And now we have to repeat that. Well, you can see immediately that A and E stay together because they're the same, B, C, D, and D is alone, and G and H are the same, H, F, D, G and H, and BF is E, F, C, in both cases BF, and C is alone, so that means that this is now the new, these are the new states, 1, 2, 3, 4, 5, this happens to be the initial state, A, so this is going to be the new initial state, so 0, 1, 2, 3, 4, and so 0, 1, 2, 3, 4 would be the states. Initial state is the one that contains the old initial state, which is 0 in this case because it contains A, capital A. And then from A, I pick 1, so 0, A, B, C, D. B is 3, C is 4, and D is 1. B, C, D, B, C, D. And then 1 is D, D is G, C, D. G is 2, C is 4, and D is 1. And then 2, I pick either one, G or D, H. It's H, F, D. H is 2, F is 3, and D is 1. And then 3 is B, E, F, C. E is 0, F is 3, and C is 4. And finally 4 is C, which is 4, 4, 4. And what is accepting? Well, 0, 1, 2 is accepting, and 3, 4 is rejecting. So this is now the reduced automaton.
Could you go over one more time how'd you get the inner numbers for like 0 and A? I'm looking at 0 location, which is A and E.
A and E, you pick any one of them. For instance, A, that gets you to B, C, D.
Yes, B, C, D.
B is in 3. C is 4. And D is 1. So you take those old states, B, C, D, and you ask, in what new state is that old state? So B is in 3. It's B, F, and so this is 3, and so there goes 3. C is, of course, just 4, so that's 4. And D is just 1, so that's it. And then you do the same.
I understand it now. Yeah, so that we follow the same one for all of them.
Yes, it's the same process.
Okay.
Okay. So we can do some more of that on Wednesday.
And so the purpose of this is to simplify the automata?
To make it the smallest possible automaton.
In the exercise set, I believe we have problem 2 is about reducing. So this would be
well,
that.
Problem 2 and problem 3 are about reducing. Problem 2, it's just reducing. In problem 3, you have a regular expression, construct an NFA, construct a DFA, and then you reduce that DFA. Okay?
Professor?
Yes?
Yeah, can you go back to slide 3 and can you explain to me again how is C concatenate with A star will give you state 0 is rejected?
Why it is rejected? Well, because you look at the initial state of the second automaton. So we do the concatenation, right? This concatenation. We concatenate this automaton for C with that automaton for A star. So we do that concatenation. We look at the initial state of the second automaton, which is accepting. So we take all the final states of the first automaton plus all non-initial final states of the second automaton.
Oh, okay, I see. Thank you.
Okay? So that gives you 0 is rejecting, and 4 and 5 are accepting.
Okay, thank you.
Sure. All right. Talk to you on Wednesday. Stay warm.
Thank you.
Bye-bye.
Thanks.